You want to start the evaluation of the DAC EV12DD700? You want to take advantage of its two channels capable of generating signals from low frequency to Ka band in multiband and simultaneously? You want to benefit of its digital features enabling unprecedented levels of dynamic RF system reconfiguration on the fly? Here is an overview of the EV12DD700 FMC EVM evaluation board giving access to the DAC 2 RF outputs and a GUI allowing to access and configure its registers. In this video, I will give you the demonstration of the capability of DAC EV12DD700 to generate two independent signals that can be time-aligned. This permits to introduce a delay in picoseconds between the two channels to take into consideration the environmental differences between the two output signals paths. Here we will compensate the mismatch due to the PCB and cables. So let's start by setting up all equipment. We are using a Teledyne Liquid LabMaster, a Rode Schwartz 20GB signal generator SMA 100NB, a marquee balloon for clock signal, marquee connectorized balloon for signal generated, one for each channel A and B, DD700 FMC product board and power supply board. FMC FPGA evaluation board is Xilinx Kintex Ultrascale KU115. In this demonstration, we will generate data that are perfectly aligned between core A and core B. This can be useful in application when environment needs to be compensated. The DAC DD700 is able to start in two configurations. First is the two cores start independently. The second is the two cores start simultaneously. For the first option, with DD700 latency first data register, user can know what value needs to be compensated to take into consideration the time gap between the two core startup. Here, in our case, we are using the second solution. The DD700's core start simultaneously, so we do not need to compensate this delay. This leaves the delay induced by the environment. The following method is proposed to compensate it and have two perfectly time-aligned signals, whatever delay is introduced by layout, connectors or cables. First step is to put the component in ramp internal test mode, then perform a sync. This ensures the startup of the two core is simultaneous. Second step is to measure on an oscilloscope the delay between the two ramps. Knowing this delay allows to write in the TX delay register of the FPGA to compensate this setup or environmental gap. The finest step delay that can be programmed is 16 times the sampling clock. Now let's get started. If not already done, plug the EV12DD700 FMC board on FPGA carrier board. Power up FPGA board. Power up power supply board of EV12DD700. Connect USB connector to the PC. Power up the board. Be aware, DAC switch must remain off. Launch the GUI. Check that in the initialization tab, the FMC board is detected. Connect SMA clock connector on clock input. Turn on clock 10.8 GHz 5 dBm. Switch the DAC switch on. Perform a software reset of the component. Enter the clock frequency, 10.8 GHz. Enable the SSO, slow synchronization output. LED 16 and 17 shall light up. It shows that the QPLL is locked. Select the 8-bit mode. Perform the eye synchronization procedure. See eye centering procedure in the user guide for more details. Select the good parameter for the loop alignment. We can see how well the sinus is defined on the LabMaster. Now, with the ramp test mode, we can see the impact of the environment on the two DAC core output and measure the delay between the two outputs. Here we have put the component in ramp mode. We can see on the lab master that the two ramps that starts not at the same time. We have measured the delay. Using this development GUI, I have access to the TX delay registers of the FPGA, and I can modify the delay value of the send sample in the FPGA. I will change the TX delay value on the GUI. Open the pattern generator and configure the desired pattern. Now we can start to configure the signal generation. In this video, we will perform a measure in the following configuration. The two DAC outputs at 215 MHz for sine wave generation. We are using low frequency so we can see better the step performs to align the signals. In a real application case, you can use every frequency reachable by the EV12DD700 to generate your signal and perform alignment using the same steps. In the GUI, we have sent to the FPGA the good value for latency between the first data. We will see the two perfectly aligned sinus. We have reached the end of this video. You have learned how to get started with the evaluation board of the EV12DD700 FMC EVM to evaluate the synchronization possibility of the two cores. The evaluation board is available so you can start your developments and test right away. If you have questions or if you are interested on the EV12DD700 FMC EVM, please contact us using Teledyne E2V hotline email address.